Hello, and welcome to the Academy of Useless Ideas. Today we are diving into the deep and fascinating world of metric spaces. But before we jump in, let's answer the million-dollar question. Why should anyone care about metric spaces? Well, for one, they provide a framework to define the convergence of sequences, which is pretty important in the world of real analysis. And to do that, we need a reliable way of calculating distances between elements in a set. That's where the metric structure of the real numbers comes in handy. And speaking of handy, let's start with the most popular way of measuring distances in the real line, the absolute value. It's like the odometer in your car, which doesn't care which directions you are headed, but it sure knows how far you are from your driveway. So let's put the absolute value to work and define the distance between two real numbers, x and y, as simply the absolute value of their difference. As mathematicians, we love breaking things down to their most essential properties. And in the realm of analysis, the essential properties of a distance function can be summarized in three key features. Firstly, the distance between any two points, x and y, is always non-negative and is only zero if x and y are identical. So it's like catching a cab. You can't get from point A to point B without paying your fare. Secondly, the distance between x and y is always the same as the distance between y and x. It's like walking or driving. It costs you the same to go back home as it does to head out. And finally, there's the triangle inequality. This tells us that the shortest distance between 2 points is a straight line. If you take any detours, you'll end up paying more. It's like taking the scenic route. Sure, it's nice to look at, but it'll cost you dearly in the end. A set equipped with a distance function is called a metric space. In metric spaces, we can understand concepts like convergence and continuity. We'll be focusing on the real numbers as a metric space with the distance function defined by the absolute value. But it's important to know that we could use other distance functions, and each function would give rise to a different version of convergence and continuity. It's like choosing your mode of transportation. A bike, a car, or a plane will all get you from point A to point B, but each will have its own set of pros and cons. Another important metric space is the vector space Rd equipped with the Euclidean distance. The Euclidean distance is what you are probably familiar with from your high school geometry class. It's a straight line distance between 2 points in a vector space. You can think of it as the repeating application of Pythagoras' theorem until you have covered all the dimensions. For example, in a two-dimensional space, the Euclidean distance between 2 points, x1, y1 and x2, y2, is simply the square root of the sum of the squares of the differences in each dimension. In a three-dimensional space, it gets a little more complicated, but the idea is the same. You just add an extra term to account for the third dimension. Although the Euclidean distance takes center stage in this discussion, we shouldn't ignore some of the other players. For instance, the taxicab distance, also known as the Manhattan distance, is like navigating the busy streets of Manhattan by adding up the absolute difference between the coordinates of 2 points. No shortcuts here, just lots of right-angle turns and traffic jams. And if that doesn't suit your taste, there's always the maximum distance or the Chebyshev distance, which measures distance by taking the largest absolute difference between the coordinates. It's kind of like a king moves in a chessboard. Now that we are familiar with metric spaces, it's time to get acquainted with open balls, an important family of sets for defining convergence and continuity. In a metric space M, an open ball is like a VIP section centered around a particular point X, with a certain radius R determining who gets to party inside. If you are outside of the radius, you are out of luck and you have to settle for the general admission section. But not all open balls are created equal. The Euclidean distance might give us the classic circular open ball. But if we switch things up and use the taxicab distance, the open ball around X looks more like a diamond. It's like we are throwing a fancy party in Manhattan, and the guests can only enter if they are within a certain number of blocks. And if we use the maximum distance, our open ball becomes a square. This is like a king hosting a party on a chessboard and only inviting the guests who are within a certain number of moves.